Hello everybody. In this video we're going to start with the last case of the one-dimensional steady-state molecular diffusion, which is the case of homogeneous reaction. So it's molecular diffusion accompanied with homogeneous reaction. And to start, I'd like to give kind of example of this system. And first we have already discussed the meaning of a homogeneous reaction. Where the reaction is taking place while diffusion or the species is diffusing. So one of the cases is that is a typical case of homogeneous first order reaction is the chemical absorption. And we have already talked about absorption before, and we said that absorption is a process where a gas mixture is contacted with a solvent, and this solvent is able to dissolve one of the component of the gas mixture, and it's industrially used a lot in many cases, such as purification of gas from contaminants, or natural gas from acid gases, or whatever. There are two cases of absorption. One of them is just to have the solvent absorbing the species without doing any changes to its chemical structure, and this is what we call the physical absorption or physisorption. And there is another case where the species that is absorbed in the solvent is reacting with the solvent. So let's say this gas mixture is air, which is the inert gas, and sulfur oxide, which is a contaminant, and you want to get rid of this contaminant, so you contact it with an absorbent which dissolves the sulfur oxide. So sulfur oxide will dissolve and will have this high concentration on this side, low concentration on this side, so it's diffusing inside towards the bulk of the solvent. And this is normal absorption, but there is a case where the sulfur oxide is reacting with the solvent itself, so it's getting consumed as it moves from here to there, and this consumption is due to reaction, which is a chemical reaction accompanied with the absorption, and that this is why we say this is chemical absorption or chemisorption. So chemisorption is a typical case of molecular diffusion. So it has high concentration here, low concentration there, so it's diffusing from here to there, and this diffusion is accompanied with chemical reaction that's consuming this species, and that's why we call it molecular diffusion with a homogeneous or homogeneous reaction. So there are some assumptions that we will make to be able to describe this process mathematically. So the first is that the concentration here is Ca node, and it's constant. You have a constant concentration of gas on the surface, and that it gets consumed from Z equals 0 until it reaches the point of Z equals delta, where the concentration is 0. So it's totally consumed at this point where it reaches Z equals delta. So the concentration here is 0, concentration here is Ca node, and we assume that the diffusion is equimolar counter diffusion. So it's not unidirectional, it's equimolar, and this is important because it will make the solution easier for us, and also it's gonna be something that we will see in the results later, and I'll come back to this point later of the equimolar counter diffusion. Finally, that or the next point is that the concentration of A here is very small, and this is another point that it's gonna make the equations more simpler. And finally, that the reaction is a first order reaction, so the reaction rate can be expressed as negative K multiplied by Ca. And this is negative equation, or the negative sign indicates that the rate is of consumption of A, so A is getting consumed. So if we check the equations that we have, the flux equation can be described by just this term of negative D multiplied by the concentration gradient, or concentration profile, and we don't have the other term for two reasons. One is we have very small concentration of A, so XA is XA here because it's liquid phase, so XA multiplied by the summation of N is 0 because XA is almost 0, and the summation of n, we have Na and Nb are equal. We have equimolar counter diffusion, so Na equals negative Nb, so we will have zero term, or the second term here is zero. So this is going to be just the flux, and the continuity equation is going to be negative dNA by dz, because it's one dimensional. I should have mentioned it here, but we have every case here in this chapter is one dimensional, so this is something that we agreed on early in this chapter. So this is going to be dNA by dz, negative dNA by dz, plus Ra, and this is the first time to see the term Ra in an equation. We always had the cases of no reaction, or a reaction where it's a heterogeneous reaction, so the reaction is a boundary condition. So this is the first time to see this term Ra part of the continuity equation. So now to substitute with the rate equation and with the flux equation, this is gonna be the shape of the continuity equation, with the assumption of constant diffusion coefficients. The negatives will cancel out, and then this is gonna be just the second derivative, and I divide the two sides of the equation by dAB. So this is the differential equation that we have and that we will use to produce the concentration profile, to get the flux and get anything we are interested in. And here comes a question, how to solve this equation. One way to solve it is to do separation of variables. So simply you would get this term to the other side in a positive sign, put Ca here and put dz squared the other side, and then try to solve it. But this is gonna be an unsuccessful way of solving this problem. The integration is going to be double integral, so it's going to be tough, and in the same time it's not going to give you the shape that you want, because the way of solving this is mathematically is different, and it's a long process. You can find it online or in any math textbooks. But anyways, this is not going to be an easy equation to solve analytically by yourself. But it is a very famous equation, and it's like very common, and you see it a lot, and people find this equation in their problems a lot, and that's why there is a general solution to this equation and to other equations. And this is what we can find in this table. This is a table of some common differential equations and their general solutions. And here you would see different forms of the equations, and this is the shape of the equation that we have in our case. It's a second derivative minus constant multiplied by the dependent variable. And this is why I put the equation in this form. I divide it by d so that the coefficient is 1, and this is the second derivative minus constant multiplied by the Ca. Of course, in our case, Ca is corresponds to y in the table, and this z corresponds to x in the table. So if you see the solution, we have two shapes of the solution, which is cosine and sine, and there is exponential of positive and exponential of negative a. So these two are two different solutions for the same problem, and of course this makes sense because cosine and sine are originally exponential functions. So cosine is exponential ax plus cosine negative ax divided by 2, and sine is the difference divided by 2. So it's more or less the same, but there are cases where it's better to use the first form, and there are cases it's better to use the second form. And the point that will make you choose which one of them is the boundary conditions. There are systems like ours which are called the definite systems, which has or finite systems, I'm sorry, where you have finite dimensions. You have a diffusion starting from point z equals 0 until z equals delta, so you have a maximum minimum points that they are already defined. So in this case it's better to go for this cosine and sine equation. There are cases which are infinite systems, so you have a case where you say that at z equals infinity the concentration equals 0, for instance. And this is a case that we will see in chapter 25, inshallah. But in these cases, if you have infinity, then cosine and sine of infinity, just to remind ourselves, this is, I'm sorry, this is sine x and this is cosine x as a function of x. They both tend to go to infinity as x goes to infinity. So if you have a boundary condition of x or z equals infinity, then sine and cosine will not help you, because if x equals infinity, then cosine infinity and sine is infinity, so the whole equation is going to be useless. But if you are using this equation, then exponential of negative infinity is 0, so this kind of makes sense and can enable us to get a solution to these problems. Anyways, just the take-home message is that this table is there. You go there, look for the equation that you have. If you have the general solution, then you are done with the integration. You don't have to bother yourself with the integration anymore. And then we will find that this is the general solution. So this is a simple thing. This table of integrals is not there in the textbook. I have already get the table here in the slides, but this table I got it from an appendix of a textbook that's called Transport Phenomena by Bird, and this has this table and other tables that you can. I mean, this table and the extension of this table. I just took this small part of this table. So it is in Appendix C, if I remember right. Yeah, this is Appendix C, table number 1. So you can find this. This table if you're interested, and the rest of the integrals. So we have the boundary conditions of z equals 0, c equals c in odd, and z equals delta, ca equals 0. So if I apply the second boundary condition, the first boundary condition, cosine of 0 is 1, sine of 0 is 0, so this is 0, this is 1, this is ca node, so c1 equals c node. And for the second boundary condition, z equals delta, so this is going to be delta, this is delta, and this is 0. So you can get c2 as a function of cosine over sine by negative sign. So this is going to be the shape of c2. And of course, this is tangent of delta square root k over d. So this is a constant. All of these arguments are constant. So this whole thing is constant. So you can substitute with C1 and C2 in this equation, and this is gonna be the concentration profile. Anyway, so this is what we have, and then we can kind of check it by seeing the concentration profile and see if the concentration profile makes sense or not. But anyways, this is the concentration profile. Now if we want to get more out of this concentration profile, and this is the check that I said, that we can see how the profile changes with different values of k delta square over d. So I rewrote the equation in terms of dimensionless parameters. So I said that this is c dash, which is c over c infinity. So if you check the equation, this is it was originally c, and we have c a node here and c e node here. So I divided the two sides, left and right hand sides, by c e node, and I divided here by delta and multiplied by delta. So I did nothing, just divided and multiplied by the same value, delta over delta, and this delta goes inside as delta square. So this is what we have here, that this is z over delta k delta square over dEb. So this is dimensionless distance, this is dimensionless concentration, and this will have a value from 0 to 1, which is very good, and z over delta will have a range of 0 to 1, which is also very good. So you have limited axis from 0 to 1, and x-axis 0 to 1 and y-axis, and then the parameter that we will change is k delta square over dEb. And this has a physical meaning, which represents the rate of reaction, which is k, divided by the rate of diffusion, which is represented by d. So you can tell if you have a very big value of k delta square over dEb, that the reaction is very fast compared to the rate of diffusion. And if you have a small value of k delta square over d, then it means that the diffusion is faster than the reaction. And this will have a very, very strong impact on the concentration profile. And this is what we see here. So we have here the normalized concentration on the y-axis and the normalized distance on the x-axis, and you see here we have different values of k delta square over dEV. I'll start here with 10,000, which is a huge number, which means that the rate of reaction is much faster than the rate of diffusion, and I'm reducing it one by one or 10 times, so it's 1,000 times, 100 times, 10 times, 1 times, until I reach 0.01. And let's check the case of k delta square over d equals 10,000, which means that you have a very fast reaction. So you'd see that the concentration drops significantly in the first 6-7% of the distance, and you almost have zero, almost, it's not exactly zero, but it's almost zero concentration here. And for the rest of the profile, you don't have any concentrations. It's consumed. And this is because the reaction is very fast, so it consumes the species very quickly. And then if you increase or reduce the k delta square over d, then it will almost behave the same way, but it will take longer distance until it reaches the concentration equals 0, and it keeps like going more in taking more distance as you go here until you reach the case of k delta square over dAV equals 0.1 or 0.01, which means that the diffusion is 100 times faster than the reaction. In this case, the profile is linear. It is a straight line, and this makes a lot of sense, because in this case the reaction is almost not contributing to the process at all. So its contribution is very minimal, and the diffusion is mainly unidirectional, equimolar counter diffusion. It is almost pure equimolar counter diffusion, which has a concentration profile of a straight line. This is what we saw before. It's a linear profile in case of an equimolar counter diffusion. So this makes a lot of sense, that the system now is almost 100% molecular diffusion with no reaction, and that's why what dominates now is the profile of the equimolar counter diffusion, and this is what we see here. So that's all for this video. In the next video we will see more about this system. And by the way, I generated these graphs myself because they are not in the textbook, but I believe that it's important to get more out of the equations, not just to get the equations and then present them as the equations. This will make you feel that there is some physical meaning and the equations make sense and this whole system is logical. So in the next video we will talk about the flux in the same system and see some other graphs as well. So I'll see you then, inshallah. Goodbye.